In this Mathematica Sessions video, we are going to do our second video on logic. But in this video, what we'll look at is valid arguments and negations. So stay tuned. For example, I can do that here. X plus y all squared, for example. And that's sometimes helpful, or I can do matrix calculations or so on. Okay, so let's begin and do this. So we've got a problem. If Peter sees some chocolate, then he will eat it. Ruth or Stuart has some chocolate. If Stuart does not have any chocolate, then Tina does not have any chocolate. All right, but let's just stop here and notice that this is not the kind of conversation that you would say over here, right? It's a little bit of a strange collection of statements. So let's just begin now to consider the symbols and write this in symbolic form. So here we've got several symbols, P, E, R, S, T, and H, to represent these things, all right? So for example, Peter sees some chocolate. We'll use the letter P to denote that. Peter eats some chocolate. We'll use the letter E to denote that one. And we're going to connect these statements with ands, ors, nots, and implies. And I've just got these written down the bottom here so that I can just copy and paste those as needed. All right, so let's go ahead and comment here. I'll just put it next to. So if Peter sees some chocolate, then he will eat it. All right, so Peter sees some chocolate, that's a P. And we have an if-then statement, so that is the implies. Let's space this out a little bit, and then he will eat it, okay? So he will eat it, that's an E, isn't it? And let's put a bracket around this, because whenever we have a sentence and a full stop and proceed to another sentence, in between those, there will be an and, all right? So this symbol down here at the bottom. All right, now let me just ask you all, are you seeing this okay? And does that work for you? Can you just say something in the chat or thumbs up? Good, great. It's good to get a little bit of feedback. And please, whenever you want to say something, just turn your mic on and just interrupt and say something. That's great. I mean, I like it when people do that because it lets us see when we need to change gears and talk about potentially something else. All right, so thanks guys. All right, so next one, Ruth or Stuart has some chocolate. Now in your toot sheet, which I'm not even showing here because I want to type directly in this and I've got all the questions written out. Okay, in your toot sheet, it says either Ruth or Stuart has some chocolate. Now that's a different statement than what we have here. Okay, now I've changed that because I've already seen the solutions and I just wanted to agree with the solutions. So that meant deleting the either that goes in front. So let's do it as is now. Ruth or Stuart has some chocolate. Okay, so R is for Ruth has some chocolate. And then an or symbol is just this one that looks like a V. All right, what was the next part? Stuart has some chocolate. So that's S. We'll put a bracket around that because later we'll put an and between these sentences. I'll just scoot it over here to the right. Okay, next one. If Stuart does not have any chocolate, then Tina does not have any chocolate. All right, so that will be a not. And in this course, I think we're using a tilde for not. So that's a not S. We have an if then. So we need an implies. And then we have a not. T for Tina has some chocolate. Okay, let's put a bracket around this. Okay, next sentence. Peter will not eat any chocolate or Stuart has some chocolate. So that's a not. Peter eats, okay, so that's a not E, isn't it? And then we need the or. or Stuart has some chocolate. Okay, so that's or S. And then bracket around this. Okay, great. So Stuart does not have any chocolate. All right, well, that's simple. That's just the tilde. So tilde and S, so not Stuart. Then we're almost at the end here. If, so this is an if and then. So we have an implies. So I'll just put that straight away. Okay, so if Peter does not see any chocolate, so that's not E, isn't it? So tilde E. And Ruth has some chocolate. So we need a wedge. I think that's called wedge, isn't it? And Ruth has some chocolate. So R. Okay, so bracket around this. So that's the conditional part. Hang on, my notes say something different, so I think maybe I read that wrong. So if Peter does not see any chocolate. Okay, so that's a not P there. Sorry guys, not P. All right, so we got that part of it correct, I think. Then everyone is happy. Okay, so that's a H for everyone is happy. So we'll put that over on the right-hand side. Okay, great. So we've got all the conditions, or sorry, all the premises written down in logic. And now let's look at the conclusion. Therefore, everyone is happy. Okay, so I'll just write the everyone is happy part, and that's just the letter H. So I'll scoot that over to the right-hand side. So we kind of at least try to line these up. Okay, so great. Now we've got all those, but what does this therefore mean? How do we join all of these together? And the way we do that is, just put that down below. Hopefully your screen is big enough that you can see it, but let me know how big your screen is and whether you can see what I'm currently writing, because that's something I don't know. I mean, laptops have different dimensions, I suppose, right? So hopefully it's okay. Okay, so let's connect all this. Now, to connect, I take the first sentence, and in between that, I put an and. All right, then I take the next sentence, and that goes after this and symbol. And now I need another and to place the next sentence. Okay, and then another and. And then the next sentence was this one, not E or S. And I need another and then not S. Okay, and then we have this one. But in between that, we need another and. Okay, good. And then that is a whole bunch of statements together, right? So now let's use a different kind of bracket. Of course, you don't have to, but it makes it easier to look at. Okay, so we can throw that. Now we have the therefore, everyone is happy. Okay, so a therefore is an if and a then. All right, so in between all that, you put implies. All right, so this is our logical statement. Now let's have a look. Is that all of the question? Write it in symbolic form, then determine whether it's valid or not. All right, great. So we've written it in symbolic form. Now let's work out whether or not it's valid. Okay, so we have to ask the question, is it possible for the statement to be invalid? Right now, you know that a P implies Q, and I'm using uppercase letters here to speak generally, is false whenever, or only when, if and only if, P is true and Q is false, right? So in other words, T implies F is the only way that is false. All right, any questions? Again, just speak up if you have any comments, remarks, or questions. I'll put this on a new line just in case people cannot see the entire screen. If you're on a phone, then maybe it reshapes that.
Hey, Seth.
I hope you're not on a phone, but we don't all have laptops or computers, right? So I guess that's a possibility. Okay, so now we're seeking out, is this possible for the premise to be true and the conclusion to be false? Okay, so what we do is we assume that we do have T implies F, and then we place values for all of the letters. Okay, so if we did, then we would have H is false, right? Because that's the conclusion here. And I'll scroll down. Okay, what else can we deduce? Now, all of these premises have to be true, right? Because they're separated by and symbols. So let's see if we can work anything out. Now, not S would have to be true, okay? So that means then that S is false. All right, good, so that not S is true. What else? Anything obvious here? Okay, I can see something. Now, since F is false and R or S has to be true, that means that R has to be true, right? Okay, good, that's something. Now, can we find anything else? Yes, I see another one. Not E or S is true, but S is false. So that says not E is true, and hence E is false, right? So E is false. Okay, good. So what else do we see? How about this one? P implies E is true under our assumption. So given that we have E is false, we cannot have P is true, right? Because if P were true, we would have a T implies F, which is false. So P has to be false. All right, now let's see, we've used this first one, we've used this, we haven't yet used this one. We've used this, we haven't used this yet. Okay, so let's see if we can use this one to get something about T, little t, lowercase t. Okay, so we know that not S is true. So we cannot have not T being false. So not T has to be true. All right, so I'll just write that. Tilde T is true. Is that correct? So hang on, let's just double check this. Not S is true. Not T has to be true because it can't be false. Okay, good. So that means that T is false. Great. All right, good. So then we need to consider this last piece. All right, so not P is true because P is false. R is true, so this part is true. Right, so this is true. Okay, that's right, isn't it? True. This, great, and R is true, so that yes, that's true. All right. However, R is true, and so we have T implies T there, given that we've got all of those things. And this is a true statement, right? Okay, so we found out that it's possible, it's indeed possible to have all the premises true while the conclusion is false. So yes, it is possible for all premises to be true while the conclusion is false. Hence, hang on, okay, so my notes say something different, that I was meant to find a contradiction. But it seems like I've written something down incorrectly. So let's go up and have another look at this. So the last statement, I thought I was meant to have a H there. Now that I peek at my notes, so let's have another look. Yeah, then everyone is happy. Okay, so I made a mistake. This should have been the letter H, so I've got some correcting to do. That's now the letter H. And so that changes things. It doesn't change this, right? But it does change this one. Okay, so H was false. Okay, good. Now we have T implies F because we're looking at this piece here. So T implies F is false, right? Okay, so let's get rid of this. So what we have now is T implies F is false. So this last one is false, but hey, it was meant to be true. Okay, so we say, but this last piece, but we assumed that this is true. And this is a contradiction. A contradiction. So the argument is in fact valid. Okay? Does that make sense? Just a thumbs up or a thumbs down if you have that option. Thumbs up, good. That's good to see. Great. And sorry, I made a little mistake with that earlier. I get a hand clap. That's good. Thank you. Okay, so let's move on to the next question. Now, if you have any comments, again, please just interrupt and say something. I guess maybe someone probably saw that I put the wrong letter there, but maybe was too timid. So please don't be timid. All right, so let's have a look at the next question here. Put some space so that we don't get confused looking at other things. Okay, so the next one says, determine whether or not the following statement is valid. So we're going to use the same technique here because we have and implies. We have several things in the premise here. We have a set of premises and then a conclusion. So premise, conclusion. All right, so let's apply the same technique. So let's assume this is invalid. Assume invalid. Okay, so I'm going to try for a moment to just type normally, because if I make this a comment, which I do with these symbols, the round bracket and then the asterisk, then it's less colorful. But the downside is that this software thinks that I'm writing some code. Okay. All right, but I'm really just typing. All right, so assume invalid. So in other words, what we're doing is we are assuming that we have a T implies F, right? So the question that we want to ask is this possible? Okay, so let's try to find out if this is possible. So if we are assuming this, then what we're doing is assuming that lowercase t is false. Okay, we are assuming, because that's here on the right-hand side, so that's the conclusion. So we're assuming that's false. We're assuming each one of these are true because they're separated by ands. Okay, so let's go through and find whether we can determine the value of one of these or any of these under that assumption. All right, so have a look. We have a not R there, so that would then be not R is true, so R has to be false. Okay, great. Now, can we see anything else? Now that we have R as false, let's have a look at this one. Q implies R. So Q implies R, that's meant to be true, but since we have the conclusion of that piece being false, that would say that we have to have Q being false, right? Because Q cannot be true, for if it were true, we would have a T implies F there, which would be false. So therefore, Q is false. Okay, great. Now let's see what else we can see. All right, how about the first piece, P or Q? P or Q, we are assuming is true, but we've determined that Q has to be false. So that would tell us then that P is true, right? Yes, P is true. Great. All right, is there anything else we can see? How about, how about this one, this piece? P and S implies T. Okay, so that's a little bit more involved, but we know that T is false. We know the entire thing is meant to be true under our assumption. So, so this part has to be false, right? Because if it were true, then the entire piece would be false. All right, so this we're assuming is false, but we have a P is true. So that tells us that S has to be false, right? So S is false. Okay, great. And now I think we haven't yet. Have we considered all of those? Not yet, okay? So let's have a look at this one. All right, so Q implies S. We've assumed that that is true, but now we have Q is false and S is false. So Q implies S is true then, right? Because the only way that that can be false is if we have T implies S. So this is true. Yes, good. Okay, so what we've deduced is, yes, it is possible. We have found values for each of the 5 letters that make the premise true while the conclusion is false. Okay, so hence it is possible to get T implies F here. And so it is invalid. Okay, do you guys agree? Thumbs up, thumbs down, or clap? Or you can say something. All right, great, good. And I'll make this a comment now that we've seen that. And then I'll backspace all of this. All right, now we can look at the next one. Let's just take a little breather and allow me to peek at the chat and see if you said anything. Okay, so, all right, so nothing special here. Jinyu says, hi, can you hear me? Jinyu, no, I wasn't able to hear you there, but maybe my volume's down. Oh, hang on, yeah, my volume was off. Sorry. Do you want to try your mic again?
Yeah, what about this time?
Okay, perfect, thank you. Yeah, great, good. Yeah, sorry guys, so the volume, my speakers were turned down too low for me to hear. All right, so hi there, hi there. Okay, isn't it not P? It should be not P and R implies H. Yeah, that's probably about the mistake that I made earlier. So let's go back and check that. Yes, that's right. That was the mistake I made earlier, so thanks for pointing that out. Okay, so I'm up to date on the chat, and so I'll go back to screen sharing unless you want to say anything else now. All right, all good. Okay, great. So where were we? Next question, write the negation of each of the following statements. All fire engines are red, some apples are ripe, a triangle with each equal sides exist. So we're going to use these symbols here. So I've got them just ready so I can copy and paste those. But I'll just write these right next to the statement. Okay, so look, I'm going a little bit too far with this one, but it gives an opportunity to introduce the symbols, okay? Because you could just straight away write the negation in English, but I suggest doing a step beyond that and writing it symbolically. So that's what I'll do here. I'll write it symbolically using these symbols. I'll negate it, and then I'll say it in English, okay? So, all right, so I'm just going to say, because we have an all here, all. And then you might choose an F for fire engine, but I'll write belonging to a set uppercase F. And then I'll write the statement, but I'll put this in English. F is red, okay? So what have I got here? So I'm saying for all fire engines, lowercase f, belonging to the set of all fire engines, uppercase F, the fire engine is red, okay? So in other words, all fire engines are red, right? Now let's negate it. So the negation is, now when we negate a simple expression like this, we change the for all into an exists. So I'll take this symbol, and then this is the same. So I'll copy and paste here, but I'll change something. F is not red. So I negate this part when I do that. So what I'm doing is I'm changing for all into exists, and I change the statement by placing a not in front of it. So I negate the statement. All right, so now that we have that, can we read this in English? There is a fire engine that is not red. Okay, so let's write that. There is a fire engine that is not red. I'm not a perfect typer, so I think I'm fast, but I'm not as fast as some people. All right, some apples are ripe. So I want you to think about that one. So you do that one. I'll just give you some time, and then we can talk about it. Okay, is that enough? Maybe. This is a little bit difficult to do when I'm not physically in the classroom with you guys. And it's also a little bit difficult when the cameras are not on and the microphones are not on. So if you want to turn on your camera and microphone, go for it. But let's just discuss it now. Some apples are ripe, okay? So some apples. Now the way to write that symbolically would be to use the exist symbol. So exist an A in uppercase A. So there's an apple in the set of apples such that A is ripe. Okay, now the negation is to change this exist into a for all. So for all A, so copy and paste here. A is or is not so. A is ripe. Okay, but how do we read this in English? Well, we read that as all, let's put this on another line. All apples are unripe. Okay, and we can see that this is false, right? Some apples are indeed ripe. All right, next one. A triangle with equal sides exists. Well, I can see straight away that that should be true, given that side lengths are permitted to be belonging to the set of all real numbers. All right, so there are, in fact, equilateral triangles. Okay, so this one's true. How do we write it symbolically? Well, we would use exist, so something like this. So there exists a triangle, lowercase t, in the set of all triangles with real sides, such that t has equal sides. Let's put equilateral, hopefully spelled that correctly. Okay, I can see there's a new chat, so I'll try to open that out. I'll stop sharing and have a peek at what someone said. All triangles does not have same side length. Okay, have I read that wrong? A triangle with equal sides exists. Okay, so you're expressing the negation in English. So let's have a look at this first. Okay, there is a triangle such that t has equal sides. Now the negation will place a for all there. Right, so the negation we know is going to be false, but let's get the for all symbol. And this would be saying t is not equilateral. You know, this spelling looks wrong. So don't trust me. I'm pretty bad at spelling, but this software doesn't do spell checking unless it's about the name of a built-in function. Okay, anyway, not a big deal. So, all right, so this would say for all triangles t is not equilateral. Okay, so let's write that out. For all triangles t.
Sorry, we can't see your screen now.
Oh, you can't see my screen. I'm so sorry. You just see my pretty face. Thank you for letting me know. You want to see my screen, not my face. Great. For all triangles t is not equilateral. Okay, good. But we know that's false, right? Because there are equilateral triangles. Okay, any comments, questions? I think we need to pick up the pace a little bit as it's 12:37. Okay, so let's have a look at the next one. 2.4. For each of the following English sentences, write in symbolic form, write the negation, and determine which one is true. So we'll have a look at A first, which says, for any rational number x and any negative integer y, there exists a real number that is greater than the product of x and y. Okay, so now you could write for all x belonging to double struct Q and y belonging to negative integers, which you could denote like this, exists z in real numbers such that z is greater than xy. Okay, or you could say this somewhat differently using a Cartesian product, which is a little bit easier from one point of view. Okay, so now I need the for all symbol, which is there. So for all x, so I'm going to use the Cartesian product here just to simplify this a little bit. But it just says for all pairs x, y belonging to the set. Now I don't have the option to get a double struct Q, so I'll just use a bold Q for rational numbers. And then I need the time symbol, but I think I might have that down here somewhere. All right, I'll just use an X for the Cartesian product here. So for all pairs of x, y, where x belongs to rational numbers and y belongs to negative integers, comma, exists z belonging to double struct R for the real numbers. And then we have z greater than the product of x and y. All right, so think about that for a moment. Is that true or false? Now what you need to know is how to read this. All right, so I read this in a particular way. What I do is I get out my lookup book, which is a lookup book containing important key things to think about in various maths courses. All right, so when you have a for all first and the exist second, right, as we do here, we have the exist second. The way you read that is this means that for all pairs x belonging to rational numbers and y belonging to negative integers, we can always find. All right, so I'm going to write that. So for all, I'll just copy this down. We can always find a real number such that z is greater than x, y. Okay, so is this true or false? Well, it's true, right? Because if you pick a rational number, just choose one, say 2/3, and a negative integer, say -5, okay, think about their product. So the product of 2/3 and -5 would be -10/3. Can I always find a real number that's greater than that? Well, yeah, of course I can, right? I could even take the floor of that number, or and add 2 to that. Okay, so that would be greater. So yes, I can definitely always find. So I'll say yes, yes, true. We can always find z. Okay, so in other words, if Jason here would choose any two numbers in these sets, could Jiangming find a z value that's greater than the product? Well, the answer is yes, right? Okay, so now we're also meant to do the negation. So let's negate this. Okay, so I'll copy this. I'll write negation. So I'll copy it, but I'll swap the symbols. So I'll put the exist there, and I'll put the for all second. And then I've got to negate this one here, but that's easy to do here because I just turn this around But when I turn it around, that's not the whole story. I need the less than or equal sign, right? Okay, so it goes like this. The negation exists for all z less than or equal to the product of x and y. But there's a special way to read that. So we read that when we have an exist first, we read that as there is a particular, okay, so write this as I say it. So there is a particular pair xy belonging to this Cartesian product such that every real number, so every real z satisfies z less than or equal to xy. Okay? So this one should be false. Right? So is there a particular pair of rational number and negative integer such that every real z is less than it? Well, no, there's not, right? And that's fairly easy to see. Okay, great. Let's scroll down and look at the next one. Okay, now I'd like you to do this one yourself, so I'll give you a little bit of time to do that. So if you have a pen and paper, write that one down. So you're writing it down symbolically. Then you're negating, you're deciding which one is true and which one is false. Okay, how are you going? Ruben, any luck? Hi, I can hear you.
So my negation is there exists x is a real number.
Okay, so there exists x belonging to the real numbers. Yeah, go on.
Any three
So the next is for all, because you said any, right? But yeah, I think you mean for all. That's fine.
any 3y equal to x.
Okay, so you need the for all part, right? So for all y belonging to real numbers. So this is the negation, correct? Such that 3y not equal to x. Is that right?
Yeah.
Okay, great. Thanks, Ruben. Okay, so did you decide whether this is true or false? You know, sometimes if you cannot decide whether one of these is true or false, it's easier to look at the other one, okay? So now this would say, the negation here would say that there is a particular real number x such that every y satisfies 3y not equal to x. Okay, is there a particular integer x? Well, the answer is no, right? So no, because if someone tries to come up with a particular real number x, I can come up with a real number y that does satisfy the equation, right? All right, so the negation here is true. Sorry, I mean the original one is true. So let's write the original one. So we put for all, and then I need the exist to go next. And then this is just an equal sign. Okay, so this one, for all real numbers x, we can always find a real number y that satisfies this. And yeah, that's correct, right? So if Ariel would choose a number, say her favorite number, is it 7, Ariel?
Sure.
Sure, okay, good, thanks. All right, so if you choose 7, well, I could say, well, Ariel, just divide it by 3, and there's a corresponding y, which is 7 over 3. That's a real number, and it satisfies that equation, right? So yes, that one is true. So yes, original is true. Okay, all good. So let's move on then, if you're ready. Okay, some of you might need to go to another class, and we're just about out of time, but for anyone who wants to stick around, you can stick around, and I'll just talk about the last question, which is 2.5. Write the negation of each of the following, then determine which is true. All right, so the first one says, for all x in real numbers, there is a real number y such that xy is 1. Okay, so that's false. This one is false because we could have x is 0, right? So in other words, if x is 0, then what we have is that 0 equals 1, which is a contradiction, right? That's false. Now we're also meant to do the negations, so let's negate this. Okay, negation. We just put the exist first, the for all second, and then this is a not equals. Okay, great. Let's have a look at the next one. B. So how do we negate this? Now, so there are 2 ways to write this, right? So I've got 2 ways to write that. So in the cheat sheet, it's as we have up in the first one, but it's easier to look at if you just write this as a Cartesian product. Okay, so negate this by changing the first one. So write negation. Change this to exist and the second one to for all. And then we just negate the last thing. Okay, so which one of these is true? All right, so the original one is true, right? For all pairs of integers x, y, we can always find an integer z such that z is equal to the difference of x and y. So x minus y. Well, that's true, right? You just take the difference and you come up with z. So true, take z equals x minus y. Okay, and that makes the negation false. Okay, now we have a part C of this, I believe, do we? Yes, we do. Have I written that? Great, it's down here. Okay, so this one says, for all x, we can always find a real number y such that this equation is satisfied. Well, yeah, that's true, right? Because, and to see that, it might help to just factor this, factorize. So I'll do that symbolically here because it's quick. All right, so this is actually just x minus 2y times x plus y is 0. Okay, so can we always find a real number y such that x minus 2y is 0 or x plus y is 0? And the answer is yes, right? So yes, we can always find a real number y such that y is equal to x over 2 or y is equal to minus x. So that's pretty clear. All right, now how about the negation? So the negation is just like this, except we change the symbols, put the exist in front and the for all second, and then we say not equals. Okay, and obviously that one is going to be false. All right, so for any x that you choose, say that Jason would choose, I can pick a corresponding y and get 0. Okay. So I'll write that for any x that you choose, I can pick y. I'll just say, for example, equal to minus x, equal to minus x, such that the expression is 0. Okay, all right, guys, so that's about it for